I've done a few videos on different mammal groups, all of them of the magnorder Boreaeutheria, until a couple months ago when I finally did one on the sister set, Atlantogenata, specifically on one of the two subsets thereof, being the superorder Aphrotheria, elephants, manatees, that sort of thing. And now we're going to talk about the other Atlantogenata superorder, Xenarthra, being a group that emerged in South America. In one way that a lot of people commonly, and I think sometimes deliberately, misunderstand evolution is by imagining that one kind of animal or whatever changes into another fundamentally different kind. That's already wrong, but they go further by supposing that all of this happens to an individual over a single lifespan, when really the development of mammals, for example, from what might seem like a more reptilian form, happened incrementally, little bit by little bit, over myriad generations and constantly branching populations. That's still going on today, fast enough that sometimes we can even see it happening. And every little bit of this sequence in the past left evidence in the form of fossils of things that are not quite mammals yet, nor are they reptiles, though they look like a blend of both. There are at least 100 or so intermediate fossil forms just for that cumulative development, which really isn't that profound a change, all things considered. It's not even just that there are intermediate fossil species for each of these stages. Rather, there are taxonomic clans of families with many species representing each of these minute increments in succession. And one of the remarkable things about the evolution of mammals is how many ancestral groups or cladistic cousins are involved throughout all of this. And the sad part is that these hundreds of intermediates represent sister sets that branched off the same lineage that led to us, but every one of those sibling groups are extinct now, too. And that's just leading up to mammals, the stages of development to become true mammals, where every other lineage faded into oblivion somewhere along the way. Then, once we were mammals, then there were several different varieties of them, where most of them are now extinct, too. And the few that remain represent a pitiful few survivors compared to how diverse each of these clades once were. That's how paleontologists see it anyway, with more genera in the fossil record than we have alive today. And all of these collective varieties proliferate to a point, and then something happens. Either some of them thin out into oblivion for their own reasons, or there's some great catastrophe that kills all of them except for, one or two surviving strains. And those one or two surviving strains blossom into another expanding group sharing whatever familial traits that the common ancestral survivor had. At one point, every type of mammal may have been warm-blooded, but not always as warm as practically all of them are now. Back then, they all laid eggs, too, which was quite a shock to the first European scientists to examine a preserved platypus. They thought it was a hoax, a taxidermic Frankenstein of different animals sewn together. But then they thought that if a god created everything however he wanted to, then why couldn't he create a mammal that laid eggs? It's not like creation has to follow any set of rules like science does. But then just a few years later, in 1827, Carl Ernst von Baer, the father of embryology, discovered the macroscopic mammalian egg in dogs first and then later in people. Imagine how that rocked the scientific community. Then by 1839, Schleiden and Schwann proposed the cell theory of biology because, cells are just a theory. And that theory has never been proven, by the way, because a scientific theory is a field of study. And how do you prove a field of study or a body of knowledge? And more importantly, it hasn't been disproven either. A cell theory, like evolution, is both a theory and a fact. We know that an egg is a single cell, that every variety of life emerges from a single cell. Then paleontology exploded as a science, and we saw fossils of semi-reptilian mammals, which were inexplicable until Darwin figured it out. And now even the platypus makes sense. The most important defining characteristic of mammals is that they produce milk. But the earliest mammals had to sweat milk out through their pores because they hadn't developed nipples yet. And while there are dozens of genera like this in the fossil record, the only representatives of that intermediate stage that are still alive today are the monotremes. That's the platypus and 3 species of echidna. That's it. As weird as those things are, things like that used to be the norm. Theirs was a much more diverse and robust group back in the Mesozoic era. Take, for example, this remarkably well-preserved fossil from the early Cretaceous, 125 million years ago. This is Simulestes xenarthrosis. The name Xenarthra is right there because of some primitive features, but this is not an ancestor of Xenarthra, although superficially it does look like the common ancestor of all therians. It has the generalized form of a shrew or an opossum, but closer inspection reveals that this is a triconodont, one of several side branches of egg-laying mammals that were already extinct before the rise of modern mammalian groups. Several intermediate taxa have gone extinct, but now we have two surviving groups, monotremes and therians, the mammals that bear live babies instead of laying eggs. There again is another division between eutherians like us, whose babies are born in a placenta, and metatherians, whose babies are born just as blind and underdeveloped fetus that has to crawl out of the womb and then climb into a pouch. You're aware of marsupials, but again, those are the only survivors. There used to be a lot more metatherians than just marsupials. So now we've got three surviving groups. We'll save metatherians for another video because that one's going to be fun. Sticking with eutherians for now, placental mammals diversified into two main groups, Boreoeutheria and Atlantogenata. Radiometric dating of fossils and estimates of the molecular clock of average mutation rates on huge data sets for both collective genomes show that this division happened way back in the late Cretaceous period of the Mesozoic era, when there were still dinosaurs. Then those groups divided again, following a branching tree pattern, where one ancestral category becomes two distinct descendant subsets, and then those go on to become four, and then eventually eight, and so on, excepting for those that ultimately go extinct. Boreoeutherians are known as the northern mammals, while Atlantogenatans emerged in the southern hemisphere. Again, this can be traced genetically among the living survivors of both groups, as well as in fossils, of course. But there are morphological cues too, physical distinctions between the northern and southern groups. The northern group, most of them anyway, share a common ancestral trait that the southern group doesn't have, and that more primitive monotremes didn't have either, but curiously, marsupials do have. So it appears that a particular developmental mutation occurred in marsupials after their divergence from the lineage leading to placentals, and then that same mutation occurred in Boreoeutherians, but later after their split from Atlantogenatans. If you don't know what I'm talking about, this peer-reviewed scientific paper should clear it up. It explains that primary testicondi represents a plesiomorphic condition for all Eutheria, as well as for all mammals. I know, right? I mean, there was another popularly accepted hypothesis for the last 100 years or so, where a particular trait emerged only once and was subsequently lost in 3 or 4 descendant groups. But this new explanation seems so obvious in retrospect. They argue that in some mammalian groups, specifically marsupialia and maybe other metatherians too, but at least marsupials and Boreoeutherians share a developmental defect where testicondi is not the norm due to a distension. They explain that during embryonic development, both testes descend from a primitive position close to the embryonic kidneys, first into the inguinal region of the lower abdomen, and then subsequently through the inguinal canals, penetrating the body wall. Thus, they actually leave the body core and become encased within a special subcutaneous diverticulum. And why you need a science communicator like me is so that I can translate all that for you, wherein all that says is that the balls drop into a sack. Northern mammals tend to carry their family jewels around in a purse for all to see. But if you follow behind one of these southern mammals, like an elephant, for example, you might never notice that something's missing. And if you look at a bull elephant from the right angle, it might look like it has 2 trunks, but you're never going to see the truck nuts, because that doesn't happen in southern mammals. That's a northern mammal thing. Boreoeutherians are also a much bigger group. They divide into Euarchontoglires like us, and Laurasiatherians, which account for most of the other mammals you can think of, the vast majority of them. But we're talking about Atlantogenatans today, the southern mammals, whose testes are as internal as their ovaries are. They divide into 2 groups too, but they're much smaller groups. Not nearly as many species, neither in fossils nor that are still around today. They are the Afrotherians, a specific lineage that emerged in Africa, and Xenarthra, another closely related group, even though they emerged in South America. Because remember that back at the end of the Mesozoic era of the dinosaurs, when these 2 groups emerged or diverged, Africa and South America had just recently broken apart and were still quite close together. Like the monotremes, which are a very small group and clearly the most primitive clade of all mammals that are still alive, Xenarthrans are also quite a small group, and they are arguably the most primitive of all Eutherian mammals. For one thing, they have the slowest metabolism of any mammal, even slower than monotremes. Everything they do is slow, including their evolution, because while they are quite different internally from every other mammal group, they haven't evolved all that much otherwise. Xenarthrans became a recognizably distinct lineage by at least 60 million years ago, according to molecular clock estimates. They show a type of dentition and a structure to their limbs and articulation of their vertebrae that are all quite unique, not seen in any other mammal group. They have a stronger lower back, allowing them to stand, sort of, so that they can use their claws for digging rather than for walking. Because apparently they all descend from an ancestral form that was initially adapted for burrowing. We mentioned in previous videos that the crown, or original form of all eutherian mammals, had a common ancestor that looked like a shrew or an opossum in the case of metatherians. For the four main groups of eutherians, think of a true shrew for laurasiatherians, a tree shrew for Euarchontoglires like us, and an elephant shrew for afrotherians. These are just to illustrate the subtle differences between their distant ancestors. Although moles seem to be among the most basal eutherians too. Moles are just shrews that went underground. Laurasiatherians have the true mole, but they're northern mammals, and we're talking about southern mammals today, like afrotherians, who had a mole form too. And it seems that Xenarthrans began from the mole form rather than the more generalized shrew form. This is indicated in the fact that Xenarthrans are all sturdily built, with strong limbs and heavy digging claws, but small eyes and poor eyesight and unicolor vision. In most of them, the genes that produce their front teeth, the canines and incisors, are dysfunctional. So if they have any teeth at all, it's usually just along the sides. And they're not molars either. They're different. They're not like the teeth of any other mammals. So they start out looking like shrews, which are insectivores. And then they became more like moles, burrowing for insects underground. Then, before they complete that transition into full-on moles, a South American variety found a more promising opportunity if they came back onto the sunlight above ground. Every clade divides into at least two daughter groups. Now, let's look at what seems to be the most primitive and generalized and least derived or specialized first. In this case, that would be pilosa. The name is Latin for hairy, so this group is named for how fluffy they are, like a fluffy pillow, pilosa. Within pilosa, of course, there are two daughter groups, and we'll look first at vermilingua, a name that means worm tongue. Although the actual animal is nowhere near as villainous as the name implies. It's just an anteater with a worm-like tongue up to 2 feet long. There are two families and 3 living genera, including the northern and southern tamandua, as well as the giant anteater. Their best defense is that massive crescent claws that are good for digging also make pretty good weapons, especially for an animal that doesn't have any teeth. They usually have thick skin and hair as well, which allows them to weather fierce attacks without taking much damage. And because they are generally slower than most other animals, another defense is that their head looks like a leg and their leg looks like a head. So if they do get attacked in an ambush, the predator might try to deliver a kill shot to one of the anteater's powerful arms, missing the head entirely and not doing any significant damage at all either, but leaving itself vulnerable to a savage counterattack from those sickle claws.
You should have gone for the head.
The remaining genus, Cyclopes, also known as the silky or pygmy anteater, is a nice example of finding indications of evolution within a living species. If you're looking for vestigial traits, look at the first, fourth, and fifth toes. They either don't have claws on them or the toes are just nubs that can't even be seen externally. But most notable, I think, are the massive hook-shaped claws on the second and third toes, which they use for hanging in the trees, just like two-toed sloths do, which, the two-toed sloth is probably the closest living relative to this thing. And today's sloths are either two-toed or three-toed, though their fossil ancestors all started with 5. And they all have these hook-shaped claws because those claws that were good for digging are also good for hanging from tree branches. The silky anteater, then, is positioned both genetically and morphologically between the terrestrial giant anteater and the arboreal tree sloth, being an intermediate form of both. So a transitional species doesn't necessarily have to be a fossil ancestor. It can be a living relative. One difference between anteaters and sloths is that anteaters don't have any teeth at all. and consequently, pioneer paleontologists in the 19th century misclassified these as Edentata, a now discarded grouping of toothless mammals that once included anteaters, pangolins, and aardvarks. But then we got the genome, which revealed that aardvarks are actually afrotheres, and pangolins, curiously, are somehow more closely related to carnivorans and ungulates than to anything toothless. So all three of these mammals lost their teeth independently and began eating ants coincidentally, there being no other options in their case. Sloths, on the other hand, don't eat ants. They are the suborder Folifora, which means that they eat leaves. So they do still have some teeth. They don't have any enamel, which is weird for teeth, but at the same time, their teeth never stop growing, which is advantageous because there's a lot more wear involved in eating leaves than in eating bugs. The problem with that is that insects are more nutritious and easier to digest than leaves. And remember that everything a sloth does is slow, even slower than anteaters. And for one thing, they have the slowest metabolism of any mammal, even slower than that of monotremes. And their body temperature is so low that they qualify as heterothermic, meaning that they barely maintain homeothermy at all and have to rely almost as much on the weather being warm all the time. They have a multi-chambered stomach, much like cattle do, and that means a long time in digestion. The snakes also are rather famous for having slow digestion, and boas have slower digestion than most snakes. Yet, it can take a sloth longer to digest 3 or 4 leaves than it would take for an adult boa to digest even a large meal, even though adult boas might only eat once a month. Their system is so slow that they eat surprisingly little, and they climb down out of their tree to poop only once a week. They're so slow that algae grows on their fur, tinting it green, and that, in combination with their slow, deliberate movements, makes it hard for predators to see them in the trees. There is even a species of moth that eats this algae and lives exclusively in sloth fur and nowhere else. Sloths are so slow that when they're on the ground, they can only crawl about 15 feet per minute. But amazingly, they can swim 3 times faster than they can crawl. You would think that something that's so slow would surely drown, but their strategy is to slow down even further. Slow down, relax, enhance your calm, get in touch with your inner Zen, your chi. And by doing this, or whatever they do, they can slow their heart rate down and their oxygen requirement along with it to such a slow point that they can hold their breath for up to 40 minutes. As strange as it is that sloths could be good swimmers, there was even a fossil sloth that was apparently semi-aquatic, having bones that were unusually heavy, typical of bottom feeders in shallow areas. Thalassocnus fossils were found associated with those of penguins, whales, and primitive seals. Thus, it was evidently inclined to feed offshore more than on land. The Pacific coast of South America was then largely desert, but just under the waves were vast fields of seagrass. That may have been an ideal setting for these sloths until they were discovered by Megalodon and the ancient whale Acrophyseter, because aquatic sloths went abruptly extinct. A seagoing sloth is a difficult thing to imagine. They also got much bigger than the sloths we have today. There were several sloths like this in the fossil record. Some were too big to climb on trees, like their contemporary cousins back then, so they were called ground sloths, which means that they necessarily would have to be faster than tree sloths, more like anteaters, because they have to fight like anteaters. Glossotherium fossils, for example, date to early in the Pliocene epoch, 3 million years ago. They were like round-bellied grazers who could rise up on 2 legs and wield those sickle claws, like a cross between a bull and a bear. They didn't wear their claws down by walking on them neither. They did more like a knuckle walk, so that as they grew at the rate that fingernails grow, they became self-sharpening. The ground sloth collective included a mountain sloth, too. Diabolotherium lived in high cliffs and dug massive burrows. It's as if these large sloths went back to acting like moles, except that some of them were then as big as bears. There were even some sloths that were as big as elephants. For example, a couple species in the Megatherium family were 20 feet long, stood 12 feet tall, and weighed 4 tons. They still weren't very fast, but they didn't need to be. They had extremely powerful limbs, bearing unusually sharp claws that were each a foot long. They only needed to hit you once. Predators had a harder time doing anything to them because they had a sort of chainmail armor in the form of hundreds of tiny bones embedded in their extra thick skin, especially in the abdominal area. So if it stood up to face down a potential threat, what's that would-be predator going to do? Just bounce off the armor and receive a death blow for its effort?
That's a death blow.
A Smilodon may have been able to take a Megatherium down with a surprise attack from above or behind, but the only other thing that could work against that is a sharpened projectile, a distance weapon like a javelin. Now, we should note that a land bridge developed between North America and South America about 3 million years ago, resulting in an interchange where South American animals like Xenarthrans, including these giant sloths, migrated into North America, and vice versa, where super predators like cats and dogs made their way into South America. And most of these fossil sloths lived from 29 million years ago to as recently as 11,000 years ago. So people who migrated to North America from Asia apparently played a part in the extinction of these massive sloths. That's the pilosa side of the Xenarthran cladogram. Now let's look at their sister clade, Cingulata. These are represented today by armadillos, 16 species in 2 families, including the 9-banded, the 6-banded, and the Brazilian 3-banded armadillo, which is the only one that can roll into a ball. Did you know that they could do that? Well, there's only one that can. And there are also hairy and fairy armadillos. Ain't they cute? And we got dwarf armadillos and giant armadillos, although the giants really aren't all that big, especially considering some of their fossil forms. There are plenty of them because, as is increasingly the case, there are more genera in the fossil record than we still have alive today. And in every instance that we've talked about so far, everything we have now has ancestral species in the fossil record that may be similar to what we have today, but they're different species nonetheless. For example, look at Peltophilus, a genus of 8 species of horned armadillo that lived from the Oligocene to late Miocene epochs, a range of 29 million to 11 million years ago. I've actually seen armadillo in quotation marks in science articles because they're an early offshoot family. They're obviously almost armadillos, if not quite armadillos, just outside of what some scientists would consider to be true armadillos, like those in the family Pamphotheridae. Those are unambiguously armadillos, though not the same as we have today. Let's look at another example, Stegotherium from the early Miocene, some 20 million years ago. Just as the pygmy anteater is an intermediate species between the ground-bound anteaters and tree sloths, so too is this thing a transitional form between an anteater and an armadillo, because it has features of both. Remember also that the giant ground sloth had osteoderms, effectively chainmail made of little bones embedded in their thickened skin. So too does the whole Cingulata clade have plates of dermal bone overlapped by keratinized epidermal scales, or scutes. And this armor typically comes in 2 parts, interrupted by bands to allow some flexibility in the middle. But that is a modern feature. Back in the old days, they didn't have that. Look at Euteitis from way back in the Paleocene to late Eocene epochs. As you can see, 40 million years ago, their shells were more rigid, not as inflexible as a turtle shell, but close. Following this theme, let's look at Glyptodonts. This is the same family as the pink fairy armadillo that we have today, and these may be their closest living relatives, but Glyptodonts are a subfamily that appear in the fossil record just over 3 million years ago, about when North America and South America reconnected. But this clade of about 32 genera is already entirely extinct, which is too bad because they're interesting. These things are like if you tried to make an ankylosaur out of a mammal. The typical theme of their armor is a dome-shaped shell, and a lot of them also wore helmets as well. But of course, what most people find most fascinating about them is how big they were. Some of them were the size of a small car. And the biggest of them, Doedicurus, had a thagomizer. What's a thagomizer, I hear you ask? It's the weapon, the spikes on the weighted cudgel at the end of their tail. Why is it called a thagomizer? Because of this cartoon from Gary Larson's strip, The Far Side. The scientific community, which is made up largely of nerds, embraced this term and use it as the official name of the spiked tail of Stegosaurus. Stegosaurs were in the same clade of armored dinosaurs as ankylosaurs, and some of their intermediate species have flattened blades rather than spikes, and some ankylosaurs independently developed tail clubs.
We need to clear something up for some of our commenters. This is a thagomizer. This is a tail club. Granted, these are informal terms, and they are similar. Both occur in thyreophorans, and both come from skin bones, but these structures evolved independently of one another. Plenty of ankylosaurs just have simple studs running all the way to their tail tip, just like their basal thyreophoran ancestors had. One recently discovered animal, a little short-tailed fella from Chile called Stegosaurus, had a third type. Like a thagomizer, it had a series of spikes pointing outwards with no handle, but like a club, the bones were fused together and surround the tail vertebrae at the tip. The authors call this a maquawheat, after the Aztec weapon. So there was experimentation with different tail armaments in different thyreophoran lineages, only one of which, the stegosaurs, developed that particular four-spike arrangement that proved so deadly to the late Thag Simmons.
Dueticurus had a spiked club on the end of its tail, and that too has been popularly regarded as a thagomizer, even though it worked more like a medieval mace. So here you have a novel trait emerging in just one species out of a family that everyone agrees are all biologically related. So Xenarthra gives us examples of the evolution of new features, and convergent evolution, beneficial mutations, vestigial traits, and of course transitional intermediate species revealing common ancestry. When you compare an anteater to a tree sloth and an armadillo, you might think that these can't be related because they look dramatically different on the surface at first. But then you see their skeletons, the particular kind of skin and hair and teeth, eyes and claws that they all had. And you look at their intermediate forms and their ancestral forms in the fossil record, and you begin to distinguish plesiomorphic or original conditions such that you can derive synapomorphies to recognize how each lineage is evolving in different directions. Because evolution is the one and only theory of biodiversity. Instead of three different kinds of animals, you begin to see them all as a continuous fluid parts in the same interconnected family tree. Thanks for watching. If you like science-oriented videos like this, then you may have noticed that they don't get the views that social or political drama does. Consequently, YouTube revenue does not adequately compensate for the time invested in this sort of content. But evolutionary phylogenies are what I prefer to show, and this is what my patrons overwhelmingly said that they prefer that I should make. So I do it for them, though there aren't really a lot of them. And every year seems to be a little tighter than the year before. If that's not your situation, and this is the type of content that you would like to see more of, then please click the link in the description and become a patron yourself. I need all the help I can get. Thank you.